Assalamualaikum. Hi guys. Today I would like to share on module number 3, topic linear programming. So the first part will be touched on special cases. There is 4 special cases in linear programming. Number 1 is infeasible problem. Second special case is unbounded problem. Number 3 is an alternate optimal solution. And number 4 is degeneracy. First special case, infeasible problem. Linear programming problem with no feasible solution, where infeasibility is a condition that arises when there is no solution to a linear programming problem that satisfies all the constraints given. Based on example number 1, consider the linear programming formulation where the objective function is maximized z equal to 2x1 and 6x2 subject to 2 constraint equation. Based on graphical method, there is no overlapping region exists, so we can conclude that there is no feasible solution. Based on simplex method, the tableau is the final table because all Cj minus Zj row are 0 and negative values. An infeasible problem is detected when an artificial variable still in the final solution mix. So, in this case, this example 1 considered as no feasible solution. Second special case, unbounded problem. The objective function value for maximization problems gets very large without bound. The objective function can increase indefinitely without reaching a maximum value. The solution space is not completely closed in. Example number 2, where the objective function is maximization and subject to 2 constraint equation where both constraint signs are greater equal. Based on graph method, solution space is not completely closed in. So example 2 considered as an example of solution is unbounded. Based on the same example, now we look at the output from simplex method. An unbounded problem is detected when all entries in the pivot column are non-positive. Hence, there will be no living variable. So, it also called as solution is unbounded. The third special case in linear programming is an alternate optimal solution. Linear programming problem has more than one optimal solution. This is the case when the objective function isoprofit or isocost line runs perfectly parallel to one of the problem's constraints, which is provide greater flexibility to the decision maker. Look at example number 3. Based on graph method, the corner point solution shows that we reach 2 optimal solution where the first solution shows that x1 equal to 30 and x2 equal to 0 with the z value is 1800, and second solution x1 equal to 20 and x2 equal to 10 also yield the z value 1800. 2 corner points having the same maximum value indicate the linear programming problem has alternate optimal solution. Based on example 3, simplex method output, all optimal solutions are detected if the final tableau has Cj minus Zj value equal to 0 for a non-basic variable. So in this example 3, for table number 1, select 2, and in table number 2, x2 is a non-basic variable with the value of 0. The last special case in linear programming is degeneracy, where a redundant constraint is one that does not affect the feasible solution region. Example number 4, we have 3 different constraints, and based on graph method, constraint number 3 considered as redundant constraint. Example 4, with simplex method output, in the first iteration, degeneracy is detected when more than one row has similar smallest non-negative number, or the value of ratio. So based on iteration number 1, choosing row S1 as the pivot row produce the following tableau. Second iteration, degeneracy causes a basic variable to have 0 value. In the second iteration, the basic variable S3 equal to 0. Lastly, in iteration number 3, in the third iteration, the basic variable X2 equal to 0 in the right hand side value. Now, we come to the second part in module 3. We will cater on sensitivity analysis. Sensitivity analysis, where sensitivity analysis is the analysis of the parameter changes on the optimal solution. Changes in resources or right-hand side value, which making changes in the resources or the right-hand side values results in changes in the feasible region and often the optimal point. This would also affect the value of the objective function. Shadow price or marginal value or dual value is the change in the value of the objective function for every additional units of the scarce resource. It is also referring to the maximum amount the firm should pay for every additional units of resources to make available. Look at example number 5. We have 2 decision variables where X1 is a CD player and X2 is a stereo receiver. So also we have 2 resources. Resource number 1 represent for electrician hour and resource number 2 represent for technician time. Based on the corner point solution, point A is an optimal solution where X1 equal to 0 and X2 equal to 20, Z equal to 2400. Now, we would like to do some sensitivity analysis by change the right-hand side value from 80 to 81 hours of electrician times available. Then, we solve the linear programming problem. Based on corner point solution, for example number 5, when we increase 1 hour in electrician hours, the optimal solution at point A, where X1 equal to 0, X2 equal to 20.25, and the Z value is 2430. It indicates that one additional unit of the electrician hour, assuming no cost incurred, cause the total profit to increase to RM2430. This is an increase of RM30. Hence, the one additional hour of electrician time is worth RM30. This is known as a shadow price for an electrician hours. The shadow price can be obtained from an optimal solution simplex tableau. There are the numbers in Cj minus Zj of slack variables column. So in this table, slack variable 1, the shadow price is RM30 for one additional hour of electrician time, and for slack 2 represent for technician time, the shadow price is RM0. So the optimal solution, X1 equal to 0 CD player, X2 equal to 20 stereo receiver, S1 equal to 0 hour of unused time of electrician, S2 equal to 40 hours of unused time of technician, and the total profit is RM 2,400.